Hey everyone, welcome back to Rock the JVM. This is Daniel, and you are watching a gentle introduction to Flink SQL. So this video is more on the data engineering and streaming side, and in this video I'm going to replicate a bit of code, and we are going to see how Flink SQL operates on an unbounded list of data. So the assumptions in this video, if you want to replicate what I'm doing here in this video, is that you have Docker and a Kotlin development environment like IntelliJ if you want to run the applications that I'm running in this video. So if you want to make the most out of this video, I recommend that you install the Docker and the GitHub repository, which you are going to find in the description to this video as a link. So clone the GitHub repository, and I'm going to walk you through what code is relevant for this video. So if you need, you can pause this video to install everything and run the code and commands with me so that you get a feel of how Flink works. And obviously, when you need to refresh your memory, just refer back to the video or to the written form at the blog. I'm also going to attach a link in the description as well, where you will find a long form article written by my old Rock the JVM student, who's now a streaming expert, Yanis Polizos. I also have an Apache Flink course here at Rock the JVM, which is a long-form course on everything that you need to master the Flink fundamentals with timestamps and watermarks and process functions and everything in between, if you want to check that out as well. So pause the video if you need to install anything and clone the GitHub repository, and I'm going to walk you through the kind of code that is relevant for us. So the project looks something like this. It's a simple Kotlin project with Gradle, and as you import it in IntelliJ, IntelliJ should download the necessary libraries for you, so you don't really need to care about that at all. And the relevant bits for us are here under the source folder and here under the Docker Compose YML, where we have two fundamental services, one for Kafka, and we also have an auxiliary service for Zookeeper to manage Kafka, and the Flink cluster, which is composed out of a job manager and a task manager. So these two work in tandem for Flink. So don't start the Docker containers just yet. So this is just the description of the Docker containers. They are already set up for you. And the source folder contains a bunch of stuff. Yanis made this repository a little bit more than we need for this video. We only need what's in the producers and the utils packages. We're going to run a simple producer which generates some fake sensor data, so like IoT data, for a Kafka cluster. So we're going to push some sensor readings to Kafka, and then we're going to read them in Flink. And on top of that, we're going to run SQL queries so that we can inspect what's happening with these sensors. So the sensor producer is a simple Kotlin file. Now, if you haven't done any Kotlin yet, don't worry, this is not really that magical. So the kind of code here is very Java-like. So the sensor producer is a simple application. And at first, we set up a few things. So we have 10 sensors and 10,000 readings in total. We have two topics, sensor.info, where we're going to push the metadata of the sensors. So we're only going to have 10 readings, basically. And the sensor.readings is the data, or the readings of the sensors. So 10 values or rows in the sensor.info topic, and sensor.readings will contain the data for all the sensors into one topic. Then we're going to generate 10 sensors, and the getSensors function is simply a loop from 0 to 10 to generate the sensor information, and the function here just returns a data structure called sensor info, where the fields sensor ID, latitude, longitude, sensor type, generation, and deployed are all faked. So we have faker, address, faker number, timestamps, and so on and so forth. So this is fictitious data for some IoT sensors. So we have 10 of those. Then we're going to set up some Kafka properties, and I decided not to type them on screen because they're quite boilerplate. So you have them in the GitHub repository if you want to steal this for your own playground. So we have the bootstrap servers, serializers, and so on and so forth. Then we're going to start two Kafka producers, one for each topic, sensor info and sensor.readings. So these two lines do that. So we have two Kafka producers. This is quite low level, but for our purposes, they will do. And then for every item in the sensor information list, we're going to call the handle message function. The handle message function is very general, and it will handle both readings from the sensor info topic and the sensor readings topic, which essentially does a producer record. So we have a parcel with that data, topic, key, and value, which sends the record to the Kafka producer in question, which we pass as an argument. So we send the record asynchronously, and as we get the metadata and the exception, this is the callback that will be invoked after the producer is done sending the record, we're going to log the exception or the success value of that particular value. So handle message basically just sends a single record to Kafka on that particular topic. So we do that for all the sensor information objects. Then we're going to generate a bunch of logs, and we're going to generate 10,000 readings in total. So for I and 0 until total sensor readings, so we have 10,000 messages. And we're going to generate a sensor reading with this data generator faker. And the generate sensor reading, again, does or returns a sensor reading data structure where the sensor ID, reading, and timestamp are always selected randomly. So the sensor ID is a random generator between 0 and the number of sensors that we have, the reading, and the timestamp, which can be the real time. And we're going to take, let's say, at most 500 milliseconds between readings. So every reading will take at most 500 milliseconds, and because we have 10,000 messages, sending all of those messages will take quite a bit of time, which will give us enough time to analyze all the data in Flink as it arrives. All right, that is the whole purpose of this little code. And we're going to do that for all the sensor readings, and we're going to simply log something every 1,000 messages, and then we're going to cleanly close the Kafka producers. So this is what our code needs to do. Now, the blog post, which may be right next to you, will contain a bunch of preamble and a bunch of subjects before getting to run the code. Now, I'm going to do the other way around. I'm going to run the code or run the commands and explain how Flink works behind the scenes as we progress. So the first thing that I'm going to do is to start a terminal here, and I'm going to start it right here in IntelliJ. You might want to start it in another window. And I'm going to run docker-compose up to spin up the Kafka cluster and the Flink cluster. Now, this may take a little while if you haven't done this before, and you can pause the video and continue after the cluster is complete. I'm going to fast forward a little bit. All right, so at this point, we have both Kafka and Flink, and I'm going to start another terminal and run my first Flink SQL command. So I'm going to say docker ps first, and we have a bunch of Docker containers here. We are going to run the job manager, which is select star from streams. This is the name of the GitHub repository - job manager. So I'm going to copy that, and I'm going to say docker exec -it, this little thing, and then I'm going to say /bin. And I'm going to use SQL-client.shell. The Docker container will automatically contain the SQL client for Flink. Ouch. I think I used the wrong names here. So it's select star from job manager. What's the name of that? So we have names. Oh, I think it's simply called job manager. So I'm going to say just docker exec-it job manager, and I'm going to run the same command. All right, now this is going to take a couple of seconds, and we have Flink SQL client already set up for us. So we have Flink SQL and a prompt. The first Flink SQL command that I'm going to run is show catalogs. Now, catalogs. What are catalogs? Catalogs are in-memory or persistent data stores that will hold the metadata for databases and tables and functions and views. So much like a regular database has metadata on the tables, so does Flink SQL with catalogs. And catalogs can be of two types. They can be in-memory, and they will be cleaned if the session is complete or if the cluster is torn down. So this is what we currently have. Or they can be persisted backed by an external system like Postgres or Pulsar or Hive, in which case they're called Postgres catalog, Pulsar catalog, and Hive catalog, and so on and so forth. Right now, we only have the default catalog, which is the in-memory catalog. Now, the persistent versions of those will give us some benefits. For example, if you have a catalog like Postgres catalog, this will enable the users of Flink SQL to automatically map tables between Postgres and Flink without you, as the Flink programmer, writing DDLs, the domain description language, in your own Flink code. The Flink Postgres connector will automatically map those tables for you, besides storing the metadata for the tables. So you have some benefits. Now, inside a catalog, we can create a database, and inside that database, we can create tables. So for example, I'm going to say create database, and I'm going to say my database, my DBL. So run that. So execute statement succeeded, and if I do show databases, I'm going to see my DBL and the default database, of course. Okay. Now, we currently have no tables, so I'm going to say show tables to prove that. So we have the empty set. Now, we also have functions. If I do show functions, now this is going to be a big table. So we have 147 different functions that we can use. We're going to see a few. All right. So we have functions, tables, and databases. We also have views, but our focus is going to be on tables. Now, I'm going to start the Kafka topics, the sensor info and sensor readings, because the Kafka cluster is fairly fresh. So I'm going to start yet another terminal window, and I'm going to run my Kafka topics command. So I'm going to say docker ps. We're going to use, we have, what's that? Select star from streams Kafka 1. This is the name. So I'm going to do docker exec -it, this little thing, and then a bash. Cool. Now I'm going to run my Kafka topics. So I'm going to say which Kafka topics. Okay, Kafka topics.shell. All right, we already have it in the path, so we can execute it directly without us having to navigate to the bin folder. So I'm going to say Kafka topics shell, and I'm going to say --create --topic. And first of all, I'm going to start up my sensor.info. So sensor info, and then partitions 1, and config, I'm going to say cleanup policy compact. So I'm going to say cleanup.policy equals compact, and bootstrap server, and I'm going to have my localhost 1992 because they're mapped to some internal Docker ports. So I'm going to say localhost 1992. All right. This will create my little topic called sensor info. I'm also going to create another topic for the sensor readings. So I'm going to say Kafka topics create. And I think I've misspelled it because this is not sensor-info, it's sensor.info. So sensor.info. I'm going to run this again. And then I'm going to delete the previous one. So Kafka topics shell --delete topic. And I'm going to say sensor-info because I've made that mistake. And my bootstrap server localhost 1992. All right, cool. So we only have sensor.info. I'm also going to run my sensor.readings. So Kafka topics create sensor.readings. And I'm going to use 3 partitions for this one. I'm going to have multiple events and bootstrap server. I'm not going to use the cleanup policy compact. I'm simply going to run the bootstrap server localhost 1992. Okay, so we have sensor.readings, and we also have sensor.info. Amazing. Now, let me run a little describe command so that I make sure that I have the right topics here. So kafka.topics, and then bootstrap server at localhost 1992, and then --describe. And we're going to see the sensor partition. So we have sensor info with 1 partition and sensor readings with 3 partitions. Awesome. Now, let me go create my appropriate table here in Flink. So here at Flink SQL, I'm going to run a create table. I'm going to say create table readings, and the readings table will have a sensor ID, which is a string. So string. I'm going to have my reading as a double. Then I'm going to have the event time, and I'm going to use the along with time zone. So I'm going to suffix that with LTZ as to timestamp LTZ from the column timestamp from Kafka. So I'm going to use that timestamp and 3. Then I'm going to have TS timestamp with 3 metadata from timestamp. And then I'm going to use the timestamp itself. So timestamp, and I'm going to use bigint. So this is going to be a long. Now I've wrapped these into backticks because they might collide with other notations from Kafka. So I'm going to have timestamp begin, and then I'm going to mark this with a watermark. So I'm going to say watermark for event time underscore LTZ as event time underscore LTZ minus interval 30 in between quotes seconds. So pretty much a natural language. And then I'm going to say with, and I'm going to pass a bunch of configs. So connector in between single quotes equals Kafka. This comes pre-built. Then I'm going to have my topic equals sensor dot readings. Then we're going to have some properties. I'm going to say properties dot bootstrap servers. This is the configuration that Flink will automatically parse to and pass to the Kafka reader. So I'm going to have localhost, or rather Kafka, colon 9092. Then I'm going to have properties, then group ID equals group sensor readings. The format is going to be JSON. So I'm going to have format is JSON. That is because this is the way that I'm serializing here in the code. So format equals JSON for the data itself. Then I'm going to have another property called scan startup. Mode equals earliest offset. So earliest dash offset. And then I'm going to have some JSON configurations here. So JSON timestamp dash format dot standard equals ISO dash 8601. Now, I don't know this off the top of my head. I have some notes next to me. So ISO 8601 for timestamp parsing, and then another one for JSON dot fail on missing field. And I'm going to say false so that I can keep Flink working even if it fails to parse something, in the off chance that it does. And then another one for JSON ignore parse errors. Again, I'm going to set that to true for the same reason. All right. So at this point, I'm going to mark the closing of the configs, and then hopefully I'm going to create the table. So execute statement succeeded. All right. Let me describe this table. So describe readings. And then we have these descriptions. So we have sensor ID string and nullable true. There's no key. Reading, double, event time LTZ, timestamp, row time 2, and this is the extras. So this is going to be the function that Flink will operate on this event time, and we have a watermark on this column. So in the Flink course, I described the situations in which it's mandatory to add watermarks for specific transformations. We have TS and timestamp to have the begin version, so the long and the timestamp. All right, good. So we have our little table. Now, let me also create another table for the sensor info metadata. So I'm going to create a table sensors. And here I'm going to have my sensor ID, which is a string. We have latitude, which is a string. So string. These are corresponding to the fields here in the sensor info data structure. So we have sensor ID, latitude, longitude, sensor type, generation, deployed. So we have longitude, which is another string. We have sensor type, which is another string, assuming I can spell properly. Generation equals string, and then we have deployed, and we have a timestamp, which I'm going to store as a long, so big int. All right. Now, I'm going to say with, and I'm going to set up some configs. So again, connector is going to be Kafka. Then we have the topic, which is sensor.info. Then we have the Kafka reader, or the Kafka subscriber properties. So properties, bootstrap servers equals, and I'm going to use Kafka column, and I need to go back to the Docker container. So I'm going to, where's that? Docker compose YML. I need 9092, and internal is 29092. So we have 29092. Then we have properties.group.id, which is again group.sensor.info. Then we have the format JSON as before, and we have my startup scan.startup mode equals earliest offset. So we have earliest offset. And the JSON properties, which is pretty much the same. So we have JSON timestamp dash format standard is going to be ISO 8601. Another one with JSON fail on parse, fail on missing field is false. And another one for fail to parse, so JSON ignore parse errors, and I'm going to set that to true. Finally, therefore completing my little description. All right, execute statement succeeded. So we have describe sensors. And at this point, we have sensor ID, latitude, longitude. These are plain columns in Flink. All right, good. Now, the most interesting table is obviously the other one because we have timestamps and watermarks, which will allow us to do joins and window functions and things of that sort. All right, so at this point, we should have everything we need to start our little sensor producers. So I'm going to navigate back to it, and I'm going to compile and run this code, which will start producing some messages to Kafka. And notice that we have some events being produced. Now we can safely go back to our little terminal and run, for example, a stateless operator, which don't require any state. For example, a projection, which is just select with a bunch of columns, and filters. So for example, I can say select sensor ID and then reading and the event time. So event time underscore LTZ from readings where reading is bigger than 40. So I can do a project, so I'm going to select a bunch of columns, and a filter where reading is bigger than 40. So when I run this little query, we're going to see every update to these tables. So we have sensor ID, we have reading, we have event time LTZ as they are being shown in Kafka. And this little application will allow us to navigate through this dynamic table. So we can do refresh, we can go to a certain page, and we can quit if we need that. So we see that table being updated in real time as events arrive at Kafka. Now, we can also materialize operators, which means that we can perform computations that are not constrained by some temporal conditions, and therefore they never complete. So the input and output records are constantly updated or deleted. For example, we can do a group by sensor ID, something like that. So in that case, the query needs to maintain state, unlike this other query that we ran before, where simply rows are appended to the table, whereas a group by will need to update internal state, and these records will be constantly updated or deleted. So for example, I can run select sensor ID and count of reading. So count of reading as total readings from readings, and then I'm going to group by sensor ID. So group by sensor ID. Now, if I run this query, notice that we have these groups being updated in real time. So we have total readings and so on and so forth. They are being updated, and these numbers will constantly grow as events arrive in Kafka. So notice that this table constantly updates every second or so. That's another kind of query that we can run. Another kind of query is a join. So for example, we can join the sensor information with the sensor reading. So the sensor info with the sensor readings table. So I can say select sensors dot sensor ID. So I'm going to differentiate the tables. So sensor ID, then I'm going to do reading, then event time LTZ, and then latitude, and then longitude, and then sensor type. And then I'm going to say from readings, join on sensors. So sensors on the join condition, the sensor ID from readings must be equal to the sensor ID from sensor. So I'm going to say readings sensor ID must equal sensors dot sensor ID. So in this case, we have a join table. And notice that every time we have a sensor ID, a reading, event time, LTZ, and latitude, and these things are constantly being updated in this table because the join will now need to take into account the new events that arrive in the readings table, and it will join that with the quote-unquote static table of the sensors because the sensors will only contain 10 rows. Now, in the case of a stateful such as a group by or a join, both tables, in this case, in the case of a join, both tables will be kept in memory, which means that the state will keep growing for both sides of the join, and therefore it's important to somehow expire the state using what is called a TTL, a time to live. A TTL is configured by table exec state TTL. This is a duration that you can set up in Flink config, and Flink will take care to expire all the rows or all the events that are being kept in memory for longer than this time duration. Now, keep in mind that there is a trade-off between accuracy and state size, because expiring state too early might result in incomplete results, so you might be joining on incomplete data. Now, another kind of operator that you can use is a temporal operator, which is constrained by time, in which case the records, that is the events, are associated with a temporal condition, for example, a time window of 30 seconds or 1 minute or something, and the records will only be accepted only within that time window, otherwise they're discarded. So state is finite in that sense because the time to live is therefore implied in the operator itself. So for example, if I want to find the 1 minute average value for each sensor, so these sensors will obviously emit multiple pieces of data through time, I can do select sensor ID, and then I'm going to take the window function parameters, which is window start, window end. These are automatically added by Flink when you do a sliding or tumbling window scheme. I'm going to show you how you can do that. And I'm going to say count of reading as total readings. So we're going to count all the readings within this time window. And I'm also going to do an average. So I'm going to say round with average of reading and 1 as average reading. And I'm going to run a tumbling window over the readings table. And the way that I'm going to do that is I'm going to say table. And I'm going to write this in all caps so that you can see the functions that I'm applying here. So table with tumble, with table readings, and the descriptor, the window descriptor for this tumbling window is descriptor by the column event time LTZ. So we're doing tumbling windows over this event time column, and the event time is always being written in the record itself. So descriptor event time LTZ, and the duration of the window, of course. So I'm going to say interval, and I'm going to have 1 minute. So this is the tumbling window function. So table readings, descriptor, whatever interval, 1 minute. Right? And then I'm going to have group by. So group by sensor ID, and then window start and window end. So for every window, for every sensor, I'm going to compute the total number of readings and the average reading. All right, let me run this. And we have for every sensor, for every window, we will have a total number of readings and an average of these. Now, as time progresses, you can check out next pages or previous pages, but because we have a 1 minute time duration, the pages will be quite few. So we have 49, and then maybe if we have another full minute, we're going to see that too. So we do have previous pages as we have events from Kafka, so I've been recording for a good few minutes now, so we have another minute being shown in this table as well. And obviously you can monitor this table as it updates. All right, so this is an example of a temporal operator that you can use. Obviously, you can also run statistics. So for example, you can run minimum, maximum, average, or standard deviation over a particular time window. And obviously, state will be only kept through that window. Now, another thing that I wanted to show you here is temporary views. So similar to database views, these can be used to store the results of a query. Now, a view is not going to be physically materialized, but instead it's run every time it's referenced in another query. And they're very useful to structure and decompose your SQL. So I'm going to run a simple example also to include some stats. So I'm going to create, so I'm going to say create view. I'm going to call this readings stats as, and then I'm going to run the query that will be run whenever I refer this reading stats. So I'm going to say select event time LTZ sensor ID. Then I'm going to say reading, and then let me run a stat like round of average. So round with average of reading over minute interval, and I'm going to define the minute interval window function shortly. So average reading over minute interval and then 1. This is the second argument to round as minute average reading. You can also do min and max, for example. So I can say max reading over the same window function. So over minute interval as min reading. You can also do max, of course. I'm going to do another round with standard deviation, so std dev of reading over the same minute interval, and then I'm going to use 5, the second argument to round, as minute std dev reading. And then I'm going to say from readings, and then I'm going to define the minute interval window function. So I'm going to say window minute interval as, and I'm going to define the minute interval window function as partition by sensor ID, order by the event time. So event time LTZ, and I'm going to say range. And this is going to be quite a complex statement here. So range between interval 1 minute, preceding and current row. Boom. And this is going to be the view. So the execute statement succeeded. Now, the only thing that I need to do now is refer this reading stats. For example, I can say select sensor ID reading and round of minute average reading plus 2 times minute std dev reading. Hopefully I can get this right. So minute std dev reading, I need to check spelling. 2, so this is the round, as, let's say, a threshold for alerting. So if I'm 2 standard deviations above the average, then I need to run some sort of notification or alert. So I'm going to say as threshold. And I'm going to have from, so I'm going to write this on another line, from readings stats. So I'm, again, materializing this view as I'm referring it into the query. Then I'm going to say where reading is bigger than minute average plus minute average reading plus twice the minute std dev reading. Hopefully that works. Now, hopefully I haven't missed anything. So notice that we have the reading and the threshold. So notice that the reading is above the threshold and grouped by sensor ID. Good. Now, as these readings proceed, we can go to next pages. And as these readings keep generating new values above the threshold over the last minute, then we can issue some sort of alert and we can notify some responsible person that is monitoring all these sensors. Hey, this particular sensor has overshot the last minute's average by 2 standard deviations. And then we can also specify the difference and decide the level of alerting if the difference is too big and so on and so forth. So we can make these decisions right in the query themselves. All right, so this was Flink SQL at a glance. I hope you enjoyed it. If you liked it, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. Check me out on Twitter and LinkedIn. I post fresh updates on upcoming material. Check out the Rock the JVM website for hundreds of hours literally on everything in the Scala ecosystem, and that includes Flink as well. Even though the video was itself written in Kotlin, you can adapt this to Java or Scala. And if you want, you can also check out the Flink course if you're interested. Until next time, folks, I'm Daniel, signing off.